In this section, we're going to be covering another rule for solving 2x2 systems, which is Cramer's rule. So suppose you have a 2x2 system, A11x plus A12y equals B1, and A21x plus A22y equals B2. And just to remind you, the subscript after A just means the row and column of the matrix. So if we converted this into matrix form, it would be A11, A12, right? Row 1, and then column 1 and column 2. And then A21, A22, row 2, column 1 and 2 respectively. And then multiplied by x and y, and then that's going to be equal to B1 and B2. So Cramer's rule is kind of like a little trick technique that you can solve 2x2 and really any system using it. But to be honest, it's not really that efficient with solving stuff that is greater than like 3x3 and 4x4. Just because row reduction kind of just does it better than anything you can think of, right? Inverse technique is fine, but there's a problem with that. Not every matrix has an inverse. And in terms of computers, they actually hate inverses because there's a lot of rounding issues. So row reduction is always king. The one advantage Cramer's rule would have is if you're doing a lot of symbolic manipulations where you're not using numbers, but rather symbols. In that case, determinants are kind of better for dealing with symbols because it's not as algebraically intensive in terms of like how it looks in terms of the manipulations. But in most cases, you're just better off doing row reduction for everything. But this technique is perfectly fine if you want to just try something a little bit different. So we have our system. As long as, and so we're going to call this matrix A, call this matrix X, and call this matrix B. As long as A is invertible, or meaning the determinant of A does not equal 0, you can apply Cramer's rule. Now, you do have to remember how to take a 2x2 determinant. So recall a 2x2 determinant of A is, so you can do vertical lines to represent your determinant, right? A11, A12, A21, A22. And so if you take the determinant, it's the top left times the bottom right minus, and very important, it is a minus, bottom left times top right. And make sure you don't get these backwards. 1, 2. And so that's our determinant. If you use A, B, C, D, then it's AD minus BC, right? It's the same thing. Just to remind you, in case you prefer to do it that way. I prefer to do it that way, so we'll just write them very quickly, AD minus BC. So, because we're going to use that in this technique. So, the rule states that you can compute the X value directly, so you don't have to do row reduction or find the inverse. You can just compute it directly by taking the determinant of A, right? So just take the determinant of A normally, and it's going to be the same thing for Y as well. The determinant of, Y is equal to something over the determinant of A. So they both have the same denominator. What changes is the numerator. And again, this is just kind of like a trick, right? So if you think about the first column, that's your X column, and then this is your Y column. Same thing over here. X column, Y column. So whatever variable you're finding, that is the column you're going to replace with the B matrix or vector. So B1, B2, and then this is A12, A22. And then for the Y variable, you're going to replace the Y column. So A11, A21, and then B1, B2. And then you just calculate the determinant on the numerator, and then that gives you your answer. And so that's Cramer's rule. So let's apply this to a system. So solve. And again, to be clear, this only works if your matrix is invertible. So if you have a matrix whose determinant is 0, then you would get division by 0, which means this technique does not work, which means row reduction. So that's to me why row reduction is the best, because it always works. Doesn't matter what technique or what matrix it is, it'll always work, and you don't have to, like, if it doesn't work, then I got to do it anyways, right? So step 1 is to write down the formula. So x is equal to, that's just a or number, the determinant of a, and then again, I prefer the A, B, C, D notation, but it's a personal preference, but I'll just do it like this. So oops, that should be B1, B2, because you replace the X variable, and then A21, nope, incorrect. A12, that's why the subscripts are always confusing. A22, and then Y is equal to, again, same bottom number. And then make sure you give yourself enough space, A21 and A11, but I said that backwards, and then B1, B2, like that. And then step 2 is to find determinant of A. And just to remind yourself, this is your B column, like that. So the values at the very end. And so A, you know what? Let's actually make step 2 to label everything. That might be better. Step 2, label matrices. So A will be equal to your numbers, so X and Y. So 2, 1, 3, -4. And then B, which is B1 and B2, that's just going to be your constants, 2 and -10. Now we can calculate the determinant of A. So that will be equal to, and if you don't like writing determinant of A, you can actually put 2 vertical lines around it, kind of like the absolute value, and it's the same thing. So again, I'll show you how that looks. So 2, 3, 1, -4. That's going to be equal to the top left times the bottom right minus 1 times 3. I do recommend that you actually write it all out, because I've seen many students just do the mental math incorrectly, like they kind of mess up the negative sign. So just be very cautious. -8 minus 3, and I get -11. Now, to remind you on how to take a determinant using a calculator, now, would you do a determinant for a 2x2? Probably not, just because you could probably do it faster by hand. But if you really want it to be safe, we do a 1x1. We put a 0 in there to make it look nice. And then from there, we do a 2x2, 2, 2. You don't include the b because you're trying to find the determinant, and you can only take the determinant of square matrices. So 2, 3, 1, -4. And then you do second quit, second matrix, hit the right arrow key, and the first option is always the determinant, at least on TI-84. Press enter, second matrix, press A, and -11, so matches what we got. So now we have that. Step 4 is to, now at this point you can plug into the formula, or you can find the X and Y determinants individually. At this point, I would just plug into formula. And so for this, I'm actually going to put it up here just to have more room. So for X, we get 11 negative. And then we're going to take the determinant of, so B1 and B2 are 2 and -10. So 2, -10. And then A1 and A2 from the original matrix is 3 and -4. And we're just going to take the determinant of that. And that's our answer. I'm just going to move this over a little bit to have more space. There we go. And from there, we get -11. And then we get 2 times -4 minus, and so you got to be careful with all of these negatives, and 3. And so we get -8. A minus minus becomes a plus 30 over -11. And so we get 22 over -11, which then gives us -2. So X is equal to -2. And then for Y, we just do the same thing, -11. But now we're going to replace the second column with the B1 and B2, so 2 and -10. And then from there, we're going to get A1, 1, and A2, 1, which is 2 and 1. which is negative 11, 2 times negative 10, minus, again, don't forget the minus sign, 1 times 2, negative 11, and so we get negative 20 minus 2 over negative 11, which is equal to negative 22 over negative 11, so y is equal to 2. So we got negative 2, positive 2, and so our answer is negative 2 comma 2. And that's essentially Cramer's rule. So from there, we think about, okay, I got a nice unique solution. What does it look like if I have something different? Like what if I have an infinite solution case? Does it change the problem? In the sense of you can't really do it. So let's see what happens. So solve. And depending on the exam and kind of the instructions, if they don't require you to use Cramer's rule, you can use whatever technique. So it may just be a case of you might have a problem that specifically says to solve using Cramer's rule. So at the very least, know the technique for a simple problem. But again, row reduction kind of does everything that you would ever want it to. But sometimes, and we'll do an example where it's kind of a decent technique just because, again, row reduction with variables is kind of annoying. So that's kind of the only case where I think it's better. So step 1, formula. Now there is an easier way of writing this entire formula, but in my experience, it's just basically condensed notation. So you kind of have to memorize what the notation is actually saying, which in this case really isn't worth it. So I would just recommend you memorize it like this. But if you feel comfortable and you don't want to have to write all of this out, there is a more condensed way of writing it using something like D and then X to tell you that it's the determinant of the X variable. So something like that. So A11, A21, B1, B2 over the determinant of A, like that. And then step 2, let's label A and B. So A is always your coefficient matrix, so that's the numbers in front of X and Y. X is almost always the first column. Y is almost always the second column. Could you reverse the order and still get the same answer? You actually could, because labels, like variables, are kind of just, they're not unique, so we could actually swap the letters, but it would just change where the answer is located, not the actual value. So we have our values, and then step 3, the determinant of A. So if we calculate the determinant of 2, -4, 6, and -12, we get 2 times -12 minus 6 times -4. And then we get -24. A negative times a negative is a positive 24, and we get 0. So this means Cramer's rule cannot be used. So basically, we have not an independent solution. So you essentially have infinite solutions. So in the context of this homework, most likely is you're just going to say not independent because you can't solve it using this technique. You would have to use row reduction. If you're wondering, what about the no solution case? Like, you get a determinant of 0? Yeah, you would get a determinant of 0 in that case, because when you have the no solution case, you essentially get a determinant of 0 since there is this thing called a free variable. So whether it's no solution or infinitely many, you will get a non-independent solution, or just can't solve it using Cramer's essentially. So the final example for Cramer's rule is just being able to solve a problem where they give you like a variable within the system, and then you might have to like solve for that variable to do something with it, right? So like I said earlier, row reduction has one weakness, which is, dealing with variables within the system is kind of frustrating because it becomes very convoluted within the matrix because you can't really get rid of it. But with Cramer's rule or even determinants, which Cramer's rule really is, it's much easier to work with. So that's like the one kind of caveat where it's actually okay. So find the solution to the system given. And so we would have 2x plus y equals 6. And then x minus, and we'll do ky equals 2. So how would I solve something for that or like that? Well, again, the technique doesn't change no matter what it looks like in terms of, variables and whatnot. So step one is, we're still copying down our formula. We're memorizing it because this is one of those things where on the exam, either you remember the formula and you can do it correctly, or you don't remember the formula and you really can't start the problem. So X column gets replaced with B1 and B2, and then the Y column gets replaced with B1 and B2 for the Y variable. So just making sure our subscripts look good. And at least the bottom is still determinant of A for both of them. And so then step two is to label A and B. So what does A equal to? It's just the numbers in front of X and Y. Now, I don't think they ever really do this to you, but they could always mix up the letters, but I have never seen that happen. But always just pay attention that X is lined up with X and Y is lined up with Y. And when you have more than two variables, sometimes you might be missing a variable. So make sure you catch that a variable is missing and you put a 0 in its spot. So we do a 1 for the top Y, and then the bottom one's going to be minus K. So now we have a variable inside of our matrix, which is kind of new, essentially. So how do we deal with that? So then step 3 is to find the determinant of A. So the determinant of A, which was 2, 1, 1K, is equal to 2 times negative K minus 1 times 1. And so I get negative 2K minus 1. That's our determinant for the denominator. And from there, we now just plug in. So step 4 is to plug in to formula. So X is equal to the determinant of B1, B2, and then 1 and negative K over negative 2K minus 1. And then this is equal to the determinant of the top over the determinant of the bottom, which we took earlier, and we get negative 6K minus 2, and then negative 2K minus 1. Now, to be very clear, some students might be tempted to simplify the 6 and the 2. When it comes to fractions, you have to be very careful with simplification. You can only simplify or cancel out terms if everything shares that term when it comes to addition and subtraction. Now, if it's multiplication, you can kind of cancel out some terms. Like if something is 6 and 2, you can divide the 6 by 2 and get 3. But when you're dealing with these, just don't simplify unless you have to in terms of like the requirement of the homework or the exam. But if you don't have to simplify, just leave it, because I'm telling you right now, you cannot simplify this one anyways, but people will try to go further because they think they have to, but you can't in this case. Also, for the homework, because I know this tends to be an issue with kind of homework syntax, if you write this as your answer on the homework, you have to put parentheses around the numerator and the denominator because the homework will not read it properly using order of operations without the parentheses. And you would be surprised how many people get it wrong, even though they did it correctly, just because of the parentheses not being there. So for those of you doing WebAssign, put parentheses on the numerator and denominator, and you should have a correct answer as long as you did it correctly. But I've seen that happen where the mistake people were making was the lack of parentheses. So A1 and A2 are there, and then we replace it with B1 and B2. So no K variable here, which is nice. So 2 times 2 minus 1 times 6 over minus 2K minus 1. And so we get 4 minus 6, which is negative 2. Again, cannot simplify that. Just leave it alone. Now, this answer is 100% correct, but sometimes they will try to make it look nicer by canceling out negatives. So if you notice, all 4 of these have a negative, so you could essentially cancel out all the negatives and make them all positive, right? You're allowed to do that. So if you look at the solution, sometimes your answer will be correct, but it's just the opposite sign. Same thing here, they cancel out all of the negatives and they get a positive, okay? So canceled out negatives. If you want to do it properly, you would factor out a -1 in front of the numerator and in front of the denominator and cancel them out. So that's how you solve for the X and Y variable. So then the question that they ask following up to this is, okay, for what value of K is there not a unique solution? So that's going to be the follow-up question. So for what value of K is there not a unique solution? Well, essentially, what they're asking you is, there is a unique solution if the determinant does not equal 0. Because if the determinant equals 0, then it's not invertible because you have division by 0. So essentially saying, what number would make the denominator equal to 0? What's the bad number, right? So essentially saying, find K value that makes denominator 0. So 2K plus 1, that equal to 0. You subtract over the 1, so you get a -1, divide over the 2, -1/2. So that's your bad number. If you plug in -1/2, then you will get division by 0, which we don't want. So every other number is perfectly fine, but for this one, you want to make sure that you don't use -1/2 because otherwise you would have division by 0. That's Cramer's rule. Again, it's just a shorthand technique to find the solution for a 2x2. Again, you can do it for a 3x3, but the problem with the 3x3 is a 3x3 determinant is so much work that by the time you do Cramer's rule for a 3x3, you probably would have done it faster using the inverse method, honestly, because if you can do Cramer's rule, then the inverse has to exist, which means then you can use the inverse method, which is arguably a little bit faster than Cramer's rule. It's probably not as accurate because you're taking the inverse, which is problematic because of rounding error. So the main lesson is row reduction is always the best technique to use.